Hi, I am Han Hu, a researcher at Microsoft Research Asia. The past year of computer vision was exciting. That we work on ongoing convergence between computer vision and natural language processing in both modeling and learning. Today, my co-worker Li Dong and I will be talking to you about two works along this theme. I will talk on the modeling part. Li Dong will present on the learning part. Our motivation comes from the unification story. Unification story has been strongly encouraged across disciplines. In physics, ground unification theory has been a holy grail. This theory tries to unify different forces, including strong, electromagnetic, weak, and gravity. This unification is highly pursued by physical scientists. For human neurons, there is also a unification story that the brain is believed to be a universal machine. The same neurons or cortexes can be trained for different human abilities. For computer vision and natural language processing, we are also witnessing unification or convergence in both modeling and learning. In modeling, the architecture are now converged to transformer variants for both NLP and CV. In the first half of this sharing, I will present Swin transformer, which is a key work towards this convergence. In learning, the two fields have been also converged to self-supervised pre-training. My colleague Li Dong will talk about an exemplified work towards this convergence, named BAIT. Let me present the first work, Swin transformer, hierarchical vision transformer using shifted windows. Before this March, the mainstream architectures in computer vision and natural language processing were largely different. In NLP, transformer has been the dominant architecture since 2017. In computer vision, convolutional neural network has been the dominant architecture for 30 years. Transformer performs very powerful in NLP. If we can have a strong general-purpose transformer architecture for computer vision, the architectures of CV and NLP will be unified or converged. Let's look at the transformer backbone in natural language processing. Given a sentence input, several transformer blocks are stacked to form a deep architecture. Each transformer block does feature transformation for each token, with the output feature of each token encoding its relationship to all other tokens. It's plain, with the same resolution at different layers. It's global, that the relationship among all tokens are computed at each layer. It also accounts for each token's absolute position. Transformer is powerful. However, to make it work well in computer vision, we need to carefully look into properties of both visual and textual signals. We first notice that a visual object can be in different scales. A fat cat is still a fat cat, no matter how large it is. In contrast, for a sentence, the words or tokens have no scale variation. We cannot say, I am a fat cat. This is invalid. Second, the visual signals are usually smooth in space. For example, these two grass patches have similar texture and they are both colored green. This property encourages a locality prior. In contrast, there is no spatial smoothness in a sentence. Thirdly, a visual object can be in different locations, which advocates translation invariance in architectural design. A fat cat is still a fat cat, no matter where it is in an image. In contrast, a word is sensitive to its location. It has different part of speech that appears at different locations. Regarding these key differences between CV and NLP, we propose Swin transformer for computer vision, which is basically a combination of transformer architecture, which has strong modeling power, and important priors for visual signals, including multi-scale, locality, and translation invariance. By these important priors, we build a bridge from NLP to computer vision. Among these important priors, I would like to particularly mention the design of locality by long-overlapping shifted windows. The long-overlapping design ensures our fast speed in real computation, particularly when compared to the traditional standing window approach. Please see this illustration. The left figure shows the locality by a traditional standing window approach. Different queries Q and Q prime will have different labeling windows, which indicates different case sets. The computation is unfriendly to memory access, and the real speed is thus not good. The right figure shows the long overlapping windows used in Swin transformer. Different queries within a same write window, for example Q and Q prime, will share a same case set. The long overlapping window approach is 3 times faster in real speed than the sliding window approach. Another important feature of this locality design is that we enable cross-window collection by shifting window partition in successive layers. Please see this illustration. In layer L, the window partitioning starts from the top left of an image. In layer L+1, the window partitioning is shifted by a half window from top to bottom and from left to right. This shifted window approach makes the non-overlapping windows as effective as the standing window method, or even better due to a regularization effect. The locality prior is in fact crucial for computer vision regarding computation complexity. It reduces the computation complexity of a linear transformer from quadratic to linear. Here is the architecture of Swin transformer. It basically follows traditional CNN backbones to have 4 stages, with each stage the same resolution as that of CNN. We maintain the resolution settings of CNN to facilitate application to existing frameworks by only replacing the backbone without a need to change the other parts. In each stage, there are repeating Swin blocks powered by a combination of the generic transformer unit and the application-specific visual priors. As a Swin transformer is a general-purpose vision backbone, it can be applied in almost all vision tasks. Here we show the results on several most important vision benchmarks. On COCO object detection, Swin transformer has surpassed previous best CNN methods by 5.3. On ADE20K semantic segmentation, Swin transformer has surpassed previous best CNN methods by 8.6. On ImageNet 1000 image classification, Swin transformer achieves 90% top-bound accuracy using 40 times less training data than VIT, a vanilla vision transformer. In fact, Swin transformer performs consistently better than CNN across the board. This table compares Swin transformer to ResNet, which is a widely used CNN backbone, by using 4 different object detection frameworks and 3 different model sets. Swin transformer performs consistently 3 to 4.5 over ResNet with similar model sets and a computation budget. Swin transformer not only works well on images, it's also the current best architecture for videos. On two major video action recognition tasks, Kinetics 400 and Kinetics 600, Swin transformer achieves the state of art. While the strong performance of Swin transformer has encouraged us to embrace transformers in computer vision, we would like to present more merits of transformers unleashed during the last 4 years by the computer vision community, summarized in 5 bullets. The first merit is that transformer possesses general modeling capability. In fact, transformers can be treated as a general graph, where all concepts and their relationships can be modeled by a graph. The concepts can be either concrete or abstract. The general modeling capability is also partly ascribed to the verification principle in building relationships between graph nodes. Please see the right illustration. No matter how different the input is, for example, the image patches in different scales and the multimodal input such as text and image patches, their relationship can be all modeled by verification in an embedding space. This general capability enables transformers to model all kinds of relationships in computer vision, such as pixel-to-pixel, object-to-pixel, and object-to-object relationship, which cover almost all vision applications. The second merit of transformer is that the transformer layer is complementary to convolution layers. Convolution is criticized as being too local, that the convolution layer has difficulty extracting long-range pixel-to-pixel dependency. Please see this illustration. For this output, even by stacking 4 layers, only pixels within a short distance are modeled. Others are not. The transformer layer is complementary to this local convolution layer, that it can see all input nodes by a single layer. The third merit of transformer lies in transformer's strong modeling power due to adaptive computation. The convolution layer is criticized to have low efficiency. In fact, convolution performs a template matching using fixed filters across all image positions. Please see this image. There are 3 boards with standardly different head poses. With a convolution layer, we need 3 channels to encode these 3 board heads, which is inefficient. Other than using fixed filters across image positions, transformer layer uses adaptive filters with the filter width determined by the composability of 2 pixels. In this way, potentially we need only 1 channel to model different board height poses. The fourth merit of transformer is its strong scalability in model size and data size. Please see this figure. The x-axis indicates a tab line. The y-axis indicates the number of model parameters. The blue curve shows quickly increased NLP model size across recent years. By scaling up NLP models, we have witnessed amazing abilities of these models. For example, the Turing model of Microsoft, the T5 model of Google, and the GPT-3 model of OpenAI. The journey of scaling up vision models just began very recently, as illustrated by the black curve. Transformer has also demonstrated strong scalability in data size, as shown in this table. The fifth merit of transformer is that it can better connect vision and language due to convergent modeling. In previous vision problems, we only have a limited number of concepts in regulation. For example, ImageNet 1000 image classification predicts 1000 categories. The per region regulation task of cocoa object detection predicts 80 categories. The per pixel regulation task of ADE20K segmentation has 150 categories. Now, thanks to the modeling convergence of NLP and CV, we can think of linking visual signals to arbitrary concepts by jointly modeling vision and NLP signals. To summarize, we would like to mention a current trend of modeling convergence between NLP and CV. Firstly, Swin transformer can serve a general purpose backbone for computer vision, designed based on a principle of a generic transformer unit and domain-specific priors. It's non-trivial to make it practical and powerful, including the use of shifted non-overlapping windows. Secondly, we argue that transformer was fully embraced by computer vision, attributed to its 5 merits, including the general modeling capability, the complementary behavior to convolution layers, the strong modeling power, the scalability in model size and data size, and the general connection between concepts and visual signals. Thank you for listening to this first part of sharing. I will leave the remaining time to my colleague, Li Dong.
Hello, everyone. I'm Li. Then I will introduce our latest work based BERT pre-training of image transformer. We turn to the denoising autoencoding idea to pre-train vision transformers, which has not been well studied by the vision community. It's challenging to directly apply BERT-style pre-training for image data. First of all, there is no pre-exist vocabulary for vision transformers input unit. image patches. So we cannot simply employ a softmax classifier to predict over all possible candidates for masked patches. In contrast, the language vocabulary, such as words and BPE, is well defined and is autoencoding prediction. A straightforward alternative is regarding the task as a regression problem, which predicts the row pixels of masked patches. However, such pixel-level recovery task tends to waste modeling capacity on pre-training short-range dependencies and high-frequency details. Our goal is to overcome the above issues for pre-training of vision transformers. We use vision transformers as our backbone architecture. We split an image into fixed-size patches, linearly embed each of them at position embeddings, and feed the resulting sequence of vectors to a standard transformer encoder. The encoder contains multiple layers of transformer blocks. The output vectors of the last layer are used as the encoded representations for the image patches. We can use a softmax classifier to perform classification by conditioning on the output vectors. Similar to natural language, we represent the image as a sequence of discrete tokens obtained by an image tokenizer instead of raw pixels. We learn the image tokenizer via discrete variational autoencoder. There are two modules during visual token learning, namely tokenizer and decoder. The tokenizer maps image pixels into discrete tokens according to a visual codebook. The decoder learns to reconstruct the input image based on the visual tokens. Because the latent visual tokens are discrete, the model training is non-differentiable. Gumball softmax relaxation is employed to train the model parameters. Then we will describe the whole-based pre-training process. The proposed self-supervised learning task is named as masked image modeling. For each input image, it has two views of representations in our method, namely image patch and visual tokens. The two tabs are used as input and output representations during pre-training. Notice the number of visual tokens and the number of image patches for one image are the same, where the correspondence relations are utilized during pre-training. Next, we randomly mask approximately 40% of image patches. Rather than randomly choosing patches for the masked positions, we employ block-wise masking in our work. For each block, we set the minimal number of patches to 16. Then we randomly choose an aspect ratio for the masking block. We repeat the above two steps until obtaining enough masked patches. The block-wise masking was also widely used in language model pre-training, which is called n-gram masking. Such mechanism can prevent short-range dependencies, which improves pre-training quality. As shown in the slides, the corresponding tokens are also masked. We then replace the masked patches with a learnable embedding. The corrupted image patches are then fed into the multi-layer transformer. The final hidden vectors are regarded as encoded representations of the input patches. For each masked position, we use a softmax classifier to predict the corresponding visual tokens. The pre-training objective is to maximize the log likelihood of the correct visual tokens given the corrupted image. The masked image modeling task is greatly inspired by the masked language modeling, which is one of the most successful pre-training objectives in natural language processing. However, directly using pixel-level autoencoding for vision pre-training pushes the model to focus on short-range dependencies and high-frequency details. It overcomes the above issue by predicting discrete visual tokens, which summarizes the details to high-level abstractions. Ablation studies show that our proposed method significantly outperforms pixel-level autoencoding. The bait pre-training can be viewed as variational autoencoder training. Let's consider the evidence lower bound of recovering the original image from its corrupted version. The first term denotes the image tokenizer that obtains visual tokens and decodes the original image given input visual tokens. In the first stage, we obtain the image tokenizer as a discrete variational autoencoder. Specifically, the first stage minimizes the reconstruction loss with a uniform prior. In the second stage, we simplify the Q function to a one-point distribution with the most likely visual tokens. Then the second term recovers the visual tokens based on the masked image, which is our masked image modeling pre-training task. It shows that our bait pre-training is well supported by variational autoencoder. Here are the pre-training setup. Which we pre-trained both base size and large size vision transformers in our experiments. After pre-training bait, we append a task layer upon the transformer and fine-tune the parameters on downstream tasks like BERT. We take image classification and semantic segmentation as examples in our work. It's straightforward to leverage the pre-training and then fine-tuning paradigm on other vision tasks with bait. For image classification task, we directly employ a simple linear classifier as a task layer. And for semantic segmentation, the bait encoder can also be end-to-end fine-tuned in a similar way. The table reports top 1 accuracy on image classification. We compare baits with vision transformers trained from random initialization, supervised pre-training, and previous self-supervised learning methods. All the compared models are base size, except LGBT has more than 1 billion parameters. Pre-training is conducted on ImageNet for the comparison purpose, except GFT is pre-trained on Google's in-house 300 million images. Compared with the models trained by random initialization, we found that pre-trained bait significantly improves performance on both datasets. The results indicate that bait can greatly reduce the requirement of annotation efforts. Bait also improves the performance on ImageNet, which shows the effectiveness under the rich resource setting. Moreover, we compare bait with previous state-of-the-art self-supervised methods for transformer, such as Dano and Moco. Our proposed method also outperforms previous self-supervised methods on ImageNet fine-tuning. We train the pre-training tasks of bait and Dano together in a multitask manner. Augmenting masked image modeling with Dano improves semantic segmentation and obtains comparable results on ImageNet classification. Moreover, bait is more effective in terms of pre-training speed, as Dano has 2 copies of transformer parameters for self-distillation and multi-crop augmentation. Because bait is also more memory efficient, we can use larger batch size to fully utilize GPU cards in practice. We further scale up bait to the large size. The results verifies the data-hungry issue of vision transformers. We're training from scratch. In comparison, the benefits of scaling up bait from base to large are greater than supervised training. The results suggest that bait tends to help more for extremely larger models, especially when labeled data are insufficient to conduct supervised pre-training for such large models. We also compare the convergence curves of the training from scratch and pre-training and fine-tuning paradigms. We find that fine-tuning bait not only achieves better performance, but also converging much faster than training DEIT from scratch. Moreover, fine-tuning baits can reach reasonable numbers within very few epochs. Then we evaluate baits on semantic segmentation. By appending a task layer based on upper net, we can fine-tune the bait backbone on the end task. Our model achieves state-of-the-art performance, even compared with previous strong methods. We conduct ablation studies to analyze the contributions of each component in bait. First, we ablate blockwise masking by randomly sample masked positions. We find that blockwise masking is beneficial on both tasks, especially on semantic segmentation. Second, we ablate the usage of visual tokens by predicting the row pixels of masked patches. For example, the pre-training task becomes a pixel regression problem to recover masked patches. Our proposed pre-training task significantly outperforms naive pixel-level autoencoding. The results indicate that the prediction of visual tokens is the key ingredient of bait. Third, we ablate the usage of visual tokens and blockwise masking together. We found that blockwise masking is even more helpful for pixel-level autoencoding, which relieves the suffering of short-distance dependency. Last, we compare baits with different training steps. Per-training the model longer can further improve performance on downstream tasks. We show that the self-attention mechanism in baits can separate objects, even though our pre-training doesn't rely on any manual annotation at all. The probing images are taken from the cocoa corpus to avoid appearing in the pre-training data. We plot the self-attention map for different reference points within an image. The visualization are produced by attention scores computed via query key product in the last layer. For each reference point, we use the corresponding patch as query and show which patch it attends to. After pre-training, base learns to distinguish semantic regions using self-attention heads without any task-specific supervision. The property partially indicates the reason why beta is able to help the downstream tasks. Such knowledge acquired by bait potentially improves the generalization ability of fine-tuned models, especially on small-scale datasets. Our contributions are summarized as follows. We propose a masked modeling image task to pre-train vision transformers in a self-supervised manner. We also provide a theoretical explanation from the perspective of variational autoencoder. We pre-train bait and conduct extensive fine-tuning experiments on downstream tasks. We present that self-attention mechanism of our methods learns to distinguish semantic regions and object boundaries, although without using any human annotation. Thanks for your listening. Here are our link and code. You can download the pre-trained model from our website.